computer. Okay, this is one of my favorite chapters in this course. The other one is ordinary differential equations, but I really love teaching this chapter, partly because I personally had an interesting journey learning about regression. I never studied statistics as an undergrad or anything that has to do with regression. We kind of just like wasn't in the curriculum, and we never were exposed to it, but I would hear about it and I was like, wow, what is this mystery? So I personally had to kind of learn it myself, and I wanted to learn it in a very intuitive and kind of understandable way. And that's why I'm excited about teaching it, because I feel that the way I learned it was very useful to me, and I hope that I can convey that usefulness to you. We will start. Trayton is saying, like and subscribe, everyone. Thank you, Trayton. That's highly recommended.
Mr. Sauter,
okay.
are these notes posted?
Let's see. So to remind you that these lectures are they're not publicly listed on YouTube. So nobody, they're just only you can see them. There are other lectures that are publicly listed where there's, no names showing, etc., but other things also on the channel. But these videos are only privately listed for you guys. Okay. All right, we will start. With the boring learning objectives, and then we'll get into the regression stuff. All right. So at the end of this chapter, you should be able to do the following. Hopefully, all of the following. Given a set of observations, compute a best fit curve or a model that minimizes the error between the model and the observation. So when we were doing interpolation, I was asked numerous times that, what if you kind of put the curve in between the points? Okay, this is that's regression. Interpolation, by definition, the interpolant is to go through each and every point and kind of give you a formula to find the points in between. Okay, so that's one aspect of curve fitting. Okay, the other aspect applies to kind of more realistic data where, one example we're going to do is predicting a person's height from their femur length. We could have the same femur length, but we could be of different heights. So that's one point on the x-axis that has two values on the y-axis, and try fitting a polynomial in there, it's not going to work. Okay, so that's why we had to more regression, because regression, as we will say over and over again, it gives you a best fit, a best curve to represent the data. Okay, define what we mean by linear regression. Conduct linear regression for polynomial models and certain nonlinear models, which is interesting. When we say linear regression, everyone thinks that it's regression to a straight line. That is not true. Linear regression, you can do a polynomial fit, you can do a cosine and logarithmic fit, and I'll show you all the little secrets there. They're all called linear regression. The only thing linear about linear regression is that you end up with a linear system of equations for the unknowns. That's why we call it all linear regression. Okay. Define and compute the mean, standard deviation, and standard error like you've never done before. Okay. Define and compute what the R-squared value, and what we mean by that. Create code in Python for linear regression. So we're going to build that from scratch, because we are going to extend regression to arbitrary models. So things that are not built in Python. So we're going to develop a technique called the normal equations to be able to do very quick regression fits for arbitrary and complex models. Define and use the normal equations to formulate linear regression. So that generalizes linear regression. Convert a nonlinear model, certain nonlinear models, into linear regression analysis, and formulate the equations for nonlinear regression. You will not be able to solve those equations yet, but you will be able to formulate those equations. Okay. All right. Our chapter begins with a story. Okay. So I'm a TV show buff. You've probably seen Bones. Not sure who's seen Bones. Have you seen Bones? Just two? Okay. It's a fun, binge-worthy show to watch. If you're a nerd like me, you would enjoy it. It's the story about this very nerdy forensic anthropologist, Emily Deschanel. She takes the role, they call her Bones, because she studies bones and what they mean regarding crime and the life of the people, she discovers the bones of. And our story begins with a forensic anthropologist. She's called to inspect a burial site, okay? I grabbed this picture off of Google. So let's pretend that, I don't know what this is, but it is some site, potentially a murder or a burial site. And, she goes in and digs up the bones, and she only finds a few bones left in that site, including a femur, the special femur. And she is tasked with identifying just the height of the individual, among a bunch of other things. You can tell a lot about the individual from their bones, just like you could tell a lot about, a tree from looking at its strings. You can tell a lot about the earth and its history by looking through, digging up samples from the earth. So she's tasked with identifying the height of the individual. Apparently, this is like a top secret thing. She only knows a few things about this, and they ask her to just get the height. And the only thing that she knows is that the femur length is 43 centimeters. Okay, I don't think actually this is a femur. I think this is an ulna maybe, but let's pretend it's a femur. That's the only picture I could find to tell this story. Okay. Now, she quickly rushes to her anthropology book and digs up some data. She remembers that, there is data that is collected across the population about a correlation, potential relation between femur length and a person's height. Turns out it is a strong predictor of a person's height, okay? So she plots the data in Python, okay? She plots the data in Python. That's the data she found. Femur length 40 centimeter, person's height 163, femur length 43. You see there's 243 data points. So at 43, there's 2 data points over here, right? And so she gets this kind of scatter plot. Person's height versus the femur length, okay? Being a good scientist who's taken numerical methods too, she attempts to fit the data using interpolation. Now, her objective is to find the person's height. The femur length was 43 centimeters, right? So at that point over here, right? So what is the person's height? Well, we really don't know. But if you do linear interpolation, this is what you get. That's wrong, right? I mean, that's just common sense. It's like, yeah, I don't think we should think of the data that way, okay? Then she goes and tries to do polynomial interpolation, and it fails miserably. Actually, if you try to do this, it's gonna crash. It's gonna tell you, yeah, I can't find the coefficients. I'm gonna find some of the coefficients. It doesn't even go through the points. I don't know what this is. I don't know what this curve is. It doesn't work. That's the point, okay? Then she steps back and thinks about the data and notices that, I'm thinking about the data differently. Instead of doing an interpolation like we did for the density and the temperature, right? Maybe we shouldn't think of it this way, as like this is the absolute truth. There is truth in there, but it's kind of a statistical sense. That truth tells us that there is a trend in the data. As the femur length increases, the height of the person tends to increase, and kind of the data are all clustered close to each other along potentially what looks like a straight line, okay, in this case, okay, sort of a straight line. So now, based on what you know so far about curve fitting, can you draw a straight line to go through more than 2 points? So based on what you know so far about interpolation, so the only thing we studied about curve fitting is interpolation. Can you draw a straight line with whatever, 20 points, 15 points? unless they're all kind of on the same line, right? Can you do that? Yeah, we can't do that. We cannot do that. Now, having taken numerical methods at the U, okay, maybe not with me, with someone else, she decides to do, actually, Professor Silcox teaches a great course on statistics, so you get to see a lot more of that in his course. But she decides to do something called regression on the data. Now, to just kind of anticipate, many of you might know what regression is. We're going to revisit that. With regression, one obtains a curve. Doesn't have to be a straight line. It's a curve. A straight line is a special case of a curve. With regression analysis, you can obtain a curve, could be a straight line, any other curve, and the formula for that curve. That's kind of the punchline here, that represents the trend of the data. Okay, what is the data doing? Capture the trend of the data rather than capturing each and every point exactly. Because if you think about it, there is a lot of error committed in measuring the femur and a person's height. So those data in the first place are not accurate. There's significant error in them. So why worry about capturing an exact formula for femur and height? Let's just capture the trend. In a statistical sense, what is the data doing? Okay. And doing that, she can draw this line with the formula y equal x plus 123.2. That's in centimeters. And then she takes that formula and plugs in 43 centimeters for the femur, and she gets a person's height of 166.2 centimeters. I forgot my tape measure at home, but on Thursday, I'm going to have some volunteers come and measure their femurs, okay, and see if the predicted height is going to correspond with your height. You know, it's a very good predictor for mine, this formula. And so that's the motivation here for studying regression. So now let's formalize what we mean by regression. The basic idea behind regression is that if you have a bunch of data points, let me turn the lights on a little bit. You have a bunch of data points that are observed, dependent variable on the y-axis, independent variable on the x-axis. Those points in practice could look like this. They're all over the place, okay? We call them the input data. And our objective is to model this data, to capture the trend of the data with a model curve. We're going to call this from now on our model curve. It could be a straight line. It could be a polynomial. It could be something else. We will learn about all of that. Okay, it's just a model curve that doesn't necessarily go through each and every point of the data, but tends to capture the general trend of the data. Okay. Now, the distance between the actual observed point and that curve, we're going to call that an error in our modeling of the data, okay? The objective of regression is to find this model curve that minimizes this distance between the points. There's a lot to be said what we mean by minimizing this error, because this error over here, there's an error here, there's an error there, there's an error there, right? So think about this curve as you're trying to kind of adjust it, its curvature, where it lies, so that you minimize the total error across all of those points. That's it. That's what regression is. The rest is all the nasty little logistics of doing the math to find that curve, okay? We will start with solving this problem by regressing to a straight line, because everything else is going to be the same. The ideas are going to be the same. The derivations are going to be identical. They just get more algebraically complex, okay? So we will start by taking only 3 points from that data set, okay? 40, 163, 41, 165, 43, 167. And our model curve now, so those are 3 points, 3 points in the plane. And our model curve is going to be A1x plus A0. It's a straight line. So we have 3 points of data scattered, okay? and I want to fit a model curve given by the formula a1x plus a0. Now, everything is red is unknown, and red is unknown, correct? Because the x data are really given to us, and the y data, we already have some y data, okay? So now our objective is to try to find a1 and a0 that such that their combination minimizes the error between the input data. So I ask a question again, how can we fit a straight line, two unknowns, into 3 or more data points? Clearly, you can fit it, you have more equations than necessary. So we need to find a mechanism to obtain 2 equations for these 2 unknowns, a1 and a0. Okay. So let's work through this together. What I'm showing up there is in these white disks with the black line around them. These are the original data points that are given to us. Okay, these are the input data. And the curve in blue with the red squares is my model curve. It's not exactly where it's supposed to be, but it's a straight line drawn across those data. Okay, and our objective is to find a1 and a0. Now I'm calling my model curve. I use this nomenclature. You don't have to use it. You can use it. Call it f model or y model. Okay, I call this y model. F of x equal a1x plus a0. Okay, now for simplicity, just for simplicity, because this is going to get complicated. Well, not too complicated. For simplicity, I'm going to call f my model curve applied for at any of the input data points xi. I'm going to call that fi. So if I take a1x plus a0 and apply it at x1 equal 40, I'm going to call that f1. Okay, and that is going to give me the red square, right? The first red square. f2 is going to be applying this model at point x2, and f3 is applying this model at point x3. Okay, just a little simplicity. So therefore, fi is simply f of xi, which is a1 xi plus a0. Okay. Okay, so that means this is f1, this is f2, and this is f3. The x values are 40, in this case 41 and 43. Now notice what I call by y are the original input data that I had. y1 is that white disk, y2 is that second white disk, and y3 is that other white disk. Okay. Now our objective is to minimize the distance between the red square and the white circle, okay, while maintaining that blue curve as a straight line. Okay, so let's see the math behind this. Okay, so the idea behind regression is to minimize the error between fi and yi. Now, what do you know? So let me ask you this. Those 3 points, they define 3 errors, right? The first error, which is the difference between y1 and f1, correct? We don't know what f is yet. Our objective is to find it, okay? But we know that there's an error between f1 and y1, and there's another error between f2 and y2, and another error between f3 and y3. What is a measure? What is an aggregate measure of an array? We did this when we measured the aggregate error of iterative solvers, right? We took the Pythagorean norm, right? The square root of the sum of these errors square, right? So I need a measure for the total error. I need an aggregate measure for the total error committed by putting this curve between these 3 input points. And that error is simply this kind of Pythagorean norm. I call it S. It's y1 minus f1 squared plus y2 minus f2 squared plus y3 minus f3 squared. Whether you take the square root or not is not an issue here. Okay, but this is still a Pythagorean norm. Okay, so now remember that. Okay, so now we have a definition for the error, and we said the idea of regression is to minimize that error. Okay, so now our objective is to minimize S. But minimize it with respect to what? Recall that F1 is A1 X1 plus A naught, and F2 is A1 X2 plus A naught, and F3 is A1 X3 plus A naught, right? Because Fi, we defined Fi to be A1 Xi plus A naught. So what happens if we substitute? Go ahead, take a moment to fill in the blanks. So take this Fi and plug it in here, okay? Work in groups and be loud. Do you guys want to work together? I don't know where there used to be a big group here, the duck. Kind of know what you're doing, but you're with these guys. Yeah, just try to plug in the F into the error equation formula. Cameron and Adeline, do you want to work together? I know there used to be another group over here. Yeah. Can you invert this? Right. Yeah. It's not an interpolant. So you put your finger on it. Because we have more equations than unknowns. We only have 2 unknowns, but you could have 100 points, right? So that's what it is. So that's why now we're going to find another way to get 2 equations with 2 unknowns. And that's what this minimization does, okay? Well, what are the coefficients? What are they? Are they A3, and where did A3 and A2 come from? Okay, think again. What is Fi? What's the only thing changing in this equation? Are the A's changing? No, right? Because it's just one line, correct? So the slope and the intercept are not going to change. But the value of that line at x1, x2, x3, right? That's changing, okay? Okay, how you guys doing? Group name? Thinking through? Okay, were you able to do the substitution? Yeah, so substitute. Okay. Mm-hmm. Correct, yeah. And so this is y1, good. Okay. Do you guys know what she's doing? Just like, she got it right, okay? She got it right. All right, how are we doing here? Okay. Oh, no, yeah, this is perfect. This is sufficient. You don't have to expand it. Right, you don't have to expand it because we're going to differentiate it now. You don't have to expand it. Yeah. Yeah. Yeah, no, this is good. Okay. Okay. Yeah, don't expand it. Just leave it in square form. Okay. 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 You don't have to expand it. Keep it in squares. Yes. Perfect. Perfect. Okay. You got it? Yes. Yes, you don't have to expand it. Just keep it in the square form. Well, you got to substitute. You can't leave xi, right? So that's applied at point 1, at point 2, at point 3, right? So it's F1, F2, and F3. Okay. Okay. All right. I have half a minute. I'll show you the answer. So all you have to do so far right now is simply take Fi and substitute it for F1 you get A1 x1 plus A naught. For F2, you get A1 x2 minus A naught. And for F3, you get A1 x3 plus A naught times the minus sign. Okay, that's all you have to do. Okay, that's all you have to do. Now is the punchline, is that now we have a new formula that tells us what the error is. And this formula has two unknowns, A1 and A naught. Now we can minimize this equation with respect to A1 and A naught. Then we get the curve, we get A1 and A naught that minimize the error. And you get two equations and two unknowns. Whether you have 1,000 points or 3 points, okay? You'll get two equations and two unknowns. We'll revisit this on Thursday, okay? And I will see you. All right, thank you.